Hello, this is Daniel. I did my project on modulation and the different effects the medium can play. So the goals for this project were to review modulating waves, so AM, PM, FM. Then I'm going to use MATLAB to perform real-time recording and processing of that audio data and perform a visual representation of the modulated waves. After that, I'm going to demonstrate standing waves. Just as an example of AM, I'm going to investigate the physical properties, such as absorption, scattering, dispersion, and attenuation. I'm also going to introduce an analysis on a yagi-uda I was working on. Also, after that, I'm going to explain the Doppler and how that affects modulation. And then at the end, I'm going to explain the trade-offs. So let's get into the review. So these are the different block diagrams. So as you can see here, this is a double sideband suppress carrier. So that is normal AM. So you have a message signal and a mixer with the carrier, and you get out normal AM. AM with carrier, it's a little different, very similar. You have that mixer, you have the carrier, but you're adding the carrier on. So you can kind of see it here, the carrier is always there. Phase modulation is just using a phase modulator. The signal, the carrier's phase is changed in accordance with the signal. Frequency modulation, it's pretty much the same thing as phase, except now the frequency is changing in accordance with the signal. So I have included these videos. These videos are from MATLAB. I created animations using my own voice, 4 different modulations, the same recording. Let's see what the difference looks like. So first we have double sideband suppressed carrier.
Hello, this is ECE 551.
Okay. Now we have with carrier.
Hello, this is ECE 551.
So you can see right there with carrier, the carrier is always present when I'm talking, as opposed to suppressed carrier,
Hello, this is ECE 551.
where when I'm not talking, it's a solid line. This is AM.
Hello, this is ECE 551.
So you can see right there the actual phase of the carrier is changing, and FM.
Hello, this is ECE 551.
And you can see that the frequency is changing.
Hello, this is ECE 551. Hello, this is ECE 551.
So as the different spectrums, so I did some FFTs of the double sideband express carrier and then spectrograms of the rest. So the main thing to take away from here is that right here, this is the baseband signal, and then we shift it up. So in the double sideband express carrier, we have the 2 bands. It's not shown here, but we have another band on the right side. And what we don't have in suppressed carrier is we don't have power at the carrier frequency. For double sideband with carrier, you can see the spectrograms clearly show that this is the baseband, lower frequency, and shifted up. And the same thing is shown throughout all of these actually. So the key takeaways, double sideband, suppressed carrier, they both waste bandwidth. It's equivalent to the message bandwidth of the signal. It's twice that. Double sideband saves more power than double sideband with carrier, because like I said before, there is no power at the carrier frequency. It's all in those 2 sidebands. For PM, the phase of the carrier is altered with respect to the amplitude. The phase sensitivity factor, Kp, affects that. For FM, it's a subset of phase modulation. And the frequency sensitivity factor, Kf, that is what affects the total frequency deviation from the center carrier frequency, which we'll see takes a key role in the attenuation through the medium. So now I'm just going to include a guitar string demo. So I'm going to show you guys an open E that I did. So here's the modulation, AM modulation. So if we look at an FFT, this is the baseband, 330 Hertz. If we go back, that is the frequency I played. This is standard tuning, by the way, just letting you know. There it is again. So the FFT clearly showed that it's 330 Hertz, at least the first harmonic, and then, or the fundamental rather. And then if you run through the AM, with my carrier frequency, it was around 20,000 Hertz, and you can see it did clearly shift it up. So creation and transmission of the waves. So how are the waves actually created? So the physics behind it. Essentially, it's just similar to a dipole. So you apply a voltage, and that voltage is going to change in accordance with the message signal that you're trying to transmit through the air. This voltage accelerates electrons to expand and compress, so as shown in the first diagram. So if you apply a voltage here, the positive side is going to want to attract to the negative, and vice versa with the positive electric field here and the negative. That kind of compresses it, which alters the electric field slightly, as seen in the second picture. If you keep on compressing it, sooner or later the actual fields are going to close, and they're going to spread out through space. So this is a GIF I found from source 3. It is very useful in actually seeing this in motion. So one thing to note, that if the charges are moving at a uniform speed, then there's really no radiation. If they're moving in a uniform speed but in a curved arc, then there is radiation. If there's oscillation, as shown here, positive, negative, then there is going to be oscillation. So wave generation, we use antennas, as we know. So this is just some common types of dipole, loop, aperture. Yagi-uda is a big one, because I'm going to actually analyze it a bit. This is a yagi-uda, so you can see it's a reflector. There's a main dipole. Sometimes it's a loop. I actually did my analysis on a dipole. And then these are driving elements. They're passive. You don't apply anything. They're just conductors. They guide the beam in the direction of the main beam here. And then this is a horn antenna. So I think this is an X-band horn antenna that I got a picture from, source 5. Some antenna characteristics, so radiation intensity, gain, power density. We've talked about this before in class. The dimensions, I just want to stress this. So the dimensions, when I do my analysis, it's all in terms of wavelengths. So let me get into it then. It'll be more concrete there. So my yagi-uda analysis. So a yagi-uda consists of a single active element and then a series of passive elements. So only the active element is being applied with the voltage signal that corresponds to the message signal we're trying to transmit. So this right here, when I did my analysis, this is my electric field vector, or matrix rather. So the orange, or the more yellowish color, that's the intensity. So it's more intense at around theta 90 and theta like 360, around that area. Or phi 360, phi 0. It'll be more concrete in the next slide. But I want to stress that my dipole length was half a wavelength. My first passive element was 0.4, and the rest, all the elements are 0.4 wavelengths. The spacing between them was 0.15 wavelength, and there was no reflector. So usually if you go back to this one, there's a reflector, right? In my analysis, there is none. Let me see. I just wanted to compare them first. So let's see. So this is what I found for the beam pattern. So here's the setup. So as I said, 0.4 for all of the passive elements, and there's 4 passive elements in my design. And then the actual dipole is half a wavelength. The distance between the passive, or each element rather, is 0.15. I found that if you lower it beneath 0.15, this main beam tends to broaden out a lot more. If you increase it, it also tends to, actually the back lobe tends to increase when you increase it. So I found this to be a sweet spot, 0.15 lambda. I want to compare this to an actual yagi-uda with a reflector in the back of it, because here we don't have one. I did not include it. I wanted to compare them. So here, as you can see, the back lobe is very much suppressed because we have that element in the back. You can kind of think of this as a transformer. Basically, these electric fields couple with this first passive element, which couples with this second element, and so on. So it kind of guides the electric field in the direction of the plane perpendicular to the passive elements. You can kind of see that here. If I did include, and if I had more time, I could have included a reflector and shown the difference. We would have gotten something very similar to this. So as we decrease the back lobe, you can see that the back lobe will kind of split up into different lobes, and that's never really good. Increases noise. Also, I want to stress that the gain of a normal one is usually about 10 dB, so around 100 times the power of a isotropic. The gain of this one, you can tell it's less than 10 dB. I did not actually calculate it, I didn't have enough time, but this, it mostly, the gain's less because of that reflector, that loss of reflector. So when optimized, a yagi-uda can be an excellent antenna that would be suitable for RF modulation. So the effects from the transmitting medium. So I am using air as the medium. I'm mostly focusing on RF. So if we look at the absorption losses in air are minimal because the resistivity is so high. Also the conductivity is very low. I mean, they're inverses, so the spreading losses follow the inverse square law. So from source 7, which is an antenna theory book I have, we can see that this is for a dipole. It does have the R square dependence for the power density. Usually when they're doing radiation intensity, they normalize that out, but it is there. So relative to isotropic, it's increasing away from the source. It'll die down as proportional to R squared, 1 over R squared. Dispersion is a major player in the attenuation of electromagnetic waves. So there's 2 types of scattering. There's Thomson scattering and then Rayleigh scattering. Rayleigh scattering we have heard of in the class. When we heard of it, it was talked about in underwater acoustic applications. It's very similar, if not the same, to RF and communicating electromagnetic waves in air. I'll explain a little further in a little bit. And then Doppler, obviously it affects the frequency of the observer. So Thomson scattering. So I did a little analysis. So assume a plane wave in the AY. It's traveling with some propagation constant K, traveling AY. E is in the Z direction. Free electron has a mass of mc. This is just an electron in the air and a charge E. If we do some force analysis, so F equals ma, so the mass times the acceleration of this particle has to be equal to the force acting on it. So here's the force, so the charge times the electric field. If we solve for z by integrating both sides, we get this. So we can kind of see that the motion in the z direction of this free particle is sinusoidal right here. Because of this, we know that it looks like a dipole. So a dipole that is moving sinusoidally, like I said before, will emit electromagnetic radiation. So basically this is taking absorbing the power of this plane wave, and then it's scattering it in a random direction that's not associated with this propagation constant. So it is losing energy that way. As for Rayleigh scattering, so as I said before, similar to underwater acoustics. So if we expand upon the problem, this is another analysis. So now this is not a free electron, it's bounded. So this is actually this is hydrogen. If we kind of do the same analyses, this is the force from the actual proton in the middle. There's a attractive force there, so that is that force. If we solve again for z, we see that it's sinusoidal, and it depends on the natural frequency of this atom. This analysis, Source 9 helped me with. It's actually really good if you want to look into that. But anyway, as we can see, as the frequency of excitation becomes much greater than the natural frequency, omega naught can be ignored. So this kind of becomes like Thompson scattering. Rayleigh scattering is highly frequency dependent and is much less than Thompson scattering. So where have we actually seen Rayleigh scattering? Well, red sunsets. So when you see a red sunset, you actually see what's left of the white light that came from the sun. Everything with higher frequency became scattered because it traveled a longer distance to get to your eyes. That's why we see orange and red and yellow in this picture, because all of the blue, violet, and green lights were scattered. That is an example of Rayleigh scattering. You might have not noticed it, but that is it. Well, that's for optical. The same thing occurs for RF frequencies. So for general scattering, Rayleigh and Thompson scattering occur and affect the transmission of RF waves. As the carrier frequencies increase, so is the Rayleigh scattering. This means that with an increased carrier frequency, attenuation will be much greater. Thompson scattering is independent of frequency, so it occurs at the same rate for each modulation technique. So what exactly does this mean in terms of the different modulation techniques we went over before? Well, we know that FM, it has a larger frequency deviation, which means that it will have a larger bandwidth, and this can cause greater attenuation and thus less range. FM already has less range, so because of the scattering it has even less. AM will have more or less the same attenuation because the frequency is not changing, it's solely the frequency of the carrier. It will have greater range compared to FM, at least in the sense of scattering, and PM is the same as AM in the regards that it's not affected greatly by it. So this is a nice picture I found from source 11 here. This is just saying how much of the actual, how much attenuation is in different bands. So this is RF band. As you can see, that's why we use the RF band. So almost 100% of everything is transmitted. There's very little attenuation. This is infrared, visible light in this band. And X-rays, as you can see, very high, but then again, they're not traveling through the air. So this is some Doppler analysis. So what happens when the receiver of the modulated wave is moving either away or towards the traveling wave? So as you can see, this is an observer. If he's traveling towards the wave or away from the wave, I did a little analysis here. This is what it comes out to be. So as you can see, it's the frequency of the wave times some constant here. Actually, it doesn't necessarily have to be a constant, but it's times some term that is dependent on the velocity of the observer and the wave. So we can see that if the velocity of the wave is much greater than the velocity of the observer, which it usually is, I'm not going to say always, because satellites, as I said here, they travel pretty quickly, not compared to the speed of light, but they still affect the modulated waves, or the observed frequency of the modulated waves. So here we can see that the effects of the Doppler from a moving receiver can be ignored because the speed relative to the speed of light is very little. So Doppler is not that much big of an effect, especially if you're driving in a car with a radio receiver. Effects from Doppler: so when the receiver is moving at high speed, the modulated signal will be received as either higher or lower frequency. And this can cause problems in narrowband receivers for AM or any really analog modulation technique. Because if it doesn't include the highest Doppler frequency, the carrier frequency will not be observed and the message will be lost. FM actually takes the largest hit because its bandwidth is already large compared to AM. And accounting for Doppler effects to increase the bandwidth even more of the passband filter at the receiver, which brings on more susceptibility of noise. So when choosing which analog modulation technique to utilize for a specific application, these trade-offs must be kept in mind. So if you increase the bandwidth, which is like we do for FM, and to account for the Doppler, you increase the attenuation, which is directly related to the relay scattering. Greater quality, which FM holds over AM, has increased bandwidth. Higher SNR, which FM does, because the message is not in the amplitude, it's in the frequency, and noise affects amplitude, not frequency. So higher SNR results in increased bandwidth. Decreased bandwidth, it has a lower SNR. Increased range has higher power. So these are just some of them. There are actually a lot more. I didn't want to go into too much detail here. But these are all the sources that I used. You can tell because the IEEE convention here. I just want to note that all graphics used were either, or that were not sourced, were from MATLAB R 2018 and iPad, and my own iPad that I took handwritten notes on from Notability. So this is my project. Thank you for listening.